Labdiena!
Labdien!
Vispirms,
Labdien!
laimīgi jauno gadu visiem!
Paldies!
Laimīgi!
Jā, paldies!
Veiksmīgu tālāko. Es sapratu, kad oficiāli jau mums ierakst, tad mēs esam gatavi sākt darbu. Šodien mums ir tāda zinātniska sapulce, vairāk seminārs, kur mēs klausīsimies savu ārzemju kolēģu zinātnisko darbu. Tas būs angļu valodā. Un pirms tam es gribu vienīgais teikt, ka par visam mūsu panākumiem un sasniegumiem akadēmijas mērogā mēs runāsim regulārajās sēdēs, kur pirmā ir pēc 18. februārī. Tātad šodien es arī noslēdzu savus ievadu vārdus un lūdzu kolēģi Juri Purānu turpināt vadīt šo te zinātnisko semināru tādā valodā, kur saprot ļoti daudz. Lūdzu, Juri.
Paldies! Hello, everybody. I'm Juris Purāns, head of Thin Film Laboratory, previously head of EXAFS Laboratory, and I'm glad to introduce you to our new members of Latvian Academy of Science. It is Professor Miroslava Dramičaņina and Dr. Jāņa Timošenko. So with two topics, interesting topic in solid state physics, one in luminescence, other in X-ray spectroscopy. And so we will start with the first one, presentation of Professor Miroslav Dramičaņina from Belgrade. I will shortly introduce you his activities, and probably you know his activities also before that it was election last year. Professor Miroslav Dramičaņina has received his PhD in Belgrade University in 1995. So his principal research, he has fellow of Institute of Nuclear Science, Vinca, in the National Institute of Republic of Serbia. So he is a full member of Faculty of Physics, University of Belgrade from 2009. So he head of Center of Excellence in photoconversation in University of Belgrade from 2020. That is very interesting, also excellent center. And deputy president of governing board of Vinca Institute of Nuclear Science from Republic Serbia from 2022. So with a broad area of activities in applied physics, optoelectronic, temperature sensor, luminescence. He has also very active pedagogical work with 15 doctoral dissertation, excellent also number of publication outstanding. He has, as I have seen, 400 publication with Hirschand index in Google Scope is about 60-64. So really very important. But for us it's important also good cooperation with our institute, 12 common publication, and with technical University of Latvia. So if it will be question additional during after presentation, and please now, Miroslav, please start your presentation and share the screen with presentation.
Thank you so much. I just want to ask you, do you see it's covering all?
Yes, it's
Okay.
your presentation we're seeing here. Please welcome.
Okay, so distinguished members of the Latvian Academy of Sciences, I would like to begin by expressing my sincere gratitude for welcoming me into the Academy and for the opportunity to share my work with you today. It's truly an honor. Today I will be discussing luminescence, a phenomenon that underlies a wide range of modern technologies, from display screens and lighting to advanced security and medical diagnostics. While luminescence has found applications across many fields, my talk will focus specifically on its powerful role in sensing. Rather than going deeply into details, I will highlight several interesting examples, mainly from my own research, with some exceptions, which I hope will serve as teasers, much like movie trailers, to spark your interest and to showcase the diversity and potential of luminescence-based sensing. So today I will talk about luminescence thermometry, example one on the ways to measure electric field via luminescence, the use of luminescence in pressure sensing, especially for aerospace research, chemical sensing with luminescence nanoparticles, nanoheaters and nanothermometers for biomedical applications. One example of use of luminescence in food analysis for the identification of botanical and geographical origin of food, and also one short example about autofluorescence as a tool for cancer diagnostics. So let's start with the luminescence thermometry. My research group works mainly with luminescence materials. About half and half is split between developing phosphors for lighting and the half for sensing. In this half, luminescence thermometry has a special role. I believe, if it's not pretentious, that my group is considered internationally as one of the groups that contribute to this field, maybe at the top level. So we are doing a lot of research in this field. And this example is also to show how collaboration, we have actually extensive network of collaboration with excellent colleagues worldwide, how this collaboration can help us. So we do a lot of luminescence thermometry mainly by ourselves, but in this example, I send my young colleagues to United States with to Professor Thomas Dunlop group to prepare thin film by pulse laser deposition, because we don't have this type of device in our house. We mainly use before powders, and do luminescence thermometry on powders, but powder is not exactly a sensor. So we thought that by making films, we can find some new applications. And when we made this film by PLD from our targets, then we return it back and do luminescence thermometry. And this is a classical example and a very successful example of luminescence thermometry that exploits intensity ratio of two emissions that comes from two adjacent excited levels of lanthanides as a measure of temperature. This type of thermometers are also called Boltzmann thermometers, because the mathematical description follows very simple Boltzmann rule. So in case of dysprosium, it can be easily excited by very strong absorption of vanadium groups in gadolinium vanadate, and then the energy transferred to dysprosium, and then these two levels serve as two emitting levels. You can see emission spectrum on this side, and this is spectrum one temperature. The ratio of these two emissions is a temperature indicator, very successful. And as you can see on this diagram, when we plot in this so-called Arrhenius type plot, since it's a Boltzmann distribution, this ratio falls on the straight line, which means that we have successful calibration. On the left side, you can see lifetime measurements. Lifetime is also, in addition to intensity ratio measurements, one of the mostly used tools to determine temperature from luminescence. However, with lanthanides, there is a wide range of temperature where lifetime of excited states does not change with the temperature, so only at high temperature it can be successfully used. So this is one example of the thermometers that can be made by making thin films that incorporates trivalent lanthanides. It can be various of trivalent lanthanides. I have a book about luminescence thermometry, which each of these lanthanides that emit a different spectral ranges is analyzed. On the next slide, you can see the basic characterization of the sensor. So it's absolute sensitivity, the relative sensitivity, the resolution or kind of uncertainty. It's a temperature that this sensor can resolve, repeatability of measurements, and values which depend on heating and cooling. So basically, we generally use this sensor today. It was successful. We have a gamma radiation facility. I know that there is one also in Latvia, and we are able to measure temperature in harsh environment, in strong radiation field, even without any excitation, because radiation field induces luminescence, and we are able to measure temperature at the places where we irradiate our samples. So the next example is how to measure luminescence or how to measure electric field with non-contact measurements of optical measurements of electric field via luminescence. Actually, it's not results of my group. It's taken from the literature. What is important, I will later tell you why it was so important for our group, but we still didn't manage to start working on this type of materials, is that if you have ferroelectric material like barium titanate, and you doped it with trivalent lanthanides. This is ytterbium-erbium is very famous upconversion pair. Ytterbium absorbs and erbium emits. In green and red spectral range. Then if you put this material inside the electric field will alter the structure of this material by forcing the titanium ions on one side and oxygen ions on the separate side. So it will alter this microcrystalline structure, the side symmetry around titanium. And it's known that ytterbium and erbium are going inside titanium site, charge compensated by negative oxygen vacancies. So this small alternation of crystal field is reflected to the amplification of the emission of erbium. In this case, we have a green emission and a red emission here, which comes from different levels. This green emission actually comes from two thermally coupled levels. I will tell you later on why it's so important. And this changes in environment around erbium in ferroelectric materials changes this ratio. As you can see here, this is the dependence of the red to green ratio, depending on the voltage that is applied to material. And then here is example. So you have this modulation, sinusoidal modulation, and this is the optical response. It's perfectly matched. So generally, this is a very good concept if you want remotely to measure electric field by optical means. And why was this so important for us is that because the ratio of green emissions here is actually one of the most famous tools to measure temperature. The erbium, trivalent erbium is the most well-known Boltzmann thermometer, luminescence Boltzmann thermometer. And since luminescence is cross-sensitive to both temperature and electric field, this type of probe is actually very good because one can use the ratio of two green emissions to correct the ratio of green to red emission, which serves as a measure of applied electric field to ferroelectrics. Let's go now to the To the second example, it's a pressure measurement via oxygen quenching of emission of pressure-sensitive paints. These are pressure-sensitive paints are actually well-known materials from 1930s. So it's mainly today organometallic compounds such as platinum porphyrins or rutetium complexes. They provide very strong and highly efficient emission, but if one embeds them inside oxygen permeable medium, some binder or even oxygen permeable polymer, then one can use luminescence to do surface measurements of the pressure on the object. So it's known that due to collisional quenching of oxygen molecules with these organometallic compounds, the intensity of emission decreases. So it's very easy to make one remote sensor that consists of illumination source and one detection camera, and to observe the surface of the object, and then to find the distribution of the pressure on the surface of that object. And why is that, for example, interesting? It's especially interesting for aerodynamics, for aerospace industry in particular. This is an example from the internet where you can find the model of the plane inside the NASA wind tunnel, which is covered with platinum porphyrin binder dye. So it's and then you have very simple detection system where you can observe changes, observe pressure on different elements of an object. So instead of making large number of discrete pressure transducers that you need to attach on different parts of your device, then with them you cannot fully have a surface mapping of your object, but also you will in some way make distortion of wind that comes to you will jeopardize aerodynamics of your object that you want to investigate. So it's a pressure tool, a very simple tool that can be used. Of course, it's researched a lot from 1960s up to now. So today you have variety of pressure-sensitive paints or different type of luminescent polymers that are used. But the main problem here is also that luminescence is also cross-sensitive to temperature, and you need to compensate for temperature fluctuations because you have increase due to friction on the object. You have increased temperature. So the main problem today is to make paints that have inside another sensor which will compensate for changes for temperature fluctuation, and also to have more sensitive paints that can then be applied not to hypervelocity tunnels or medium velocity tunnels, wind tunnels, but also for low velocity tunnels, which serves as aerodynamic tools for improving aerodynamics of, let's say, personal cars and vehicles, trucks, trains, and so on. So it's when you have this type of surface measurements of pressure on your object and with new tools for modeling, then one can improve aerodynamics of vehicles, and then this will serve as an excellent way to save energy, which is crucial today. We have a nice project with ONERA. It's a French aerospace agency and Technical University of Graz to develop this new paint. I cannot show the details. It's classified, unfortunately, until June when we will do the final testing. Our part of the research was to develop a sensor based on lifetime measurements, and we developed mangan 4+ based sensor. On the left side, you can see the real measurements of temperature resolution or of accuracy and precision, which are made in the big barrel filled with water, highly isolated, so it's supposed to keep the temperature constant, and then you can see this fluctuation. Actually, these two lines represent the resolution of our measurements. So this between these oscillation, the precision does not exist, but it's 0.01 Kelvin, and even more, the response of this optical sensor compared to the standard platinum electric thermometers, it's almost instant, which is amazing. And also Austria, the Graz and the group from Graz are doing excellent. I know that they already finished their part of research, so I'm hardly waiting June when we have scheduled testing in France. So it's not easy today to get time for measurements in this type of wind tunnels, but I hope that the results will be very good. So chemical sensing, and here I want to mention the late Professor Otto Wolfbeis. He's a really amazing professor and friend. He is Austrian from Graz, but he was for many years director of University of Institute for Bioanalytical Chemistry in Regensburg. He has so many excellent students today that are working around the world. He has Hirsch index above 100, 7 spin-off companies. So he was editor of Angewandte Chemie for many years and some other journals. And we did this research many years ago with his supervision, actually, using nanoparticles to sense chemical analytes. It was well-known field, but mostly semiconducting quantum dots were used at that time. And we developed gadolinium vanadate nanoparticles, which were only a few nanometers in size, and they are not cross-sensitive to environment. They are only sensitive to hydrogen peroxide. They quench the emission under hydrogen peroxide. And when he saw our results, he offered his help to guide us to start this field. And I will show you why this field is so important. So these are classical excitation and emission spectra of europium-3+. The spectra are broad because europium is embedded in very small nanoparticles. It's mainly because of that this europium-3+ is on the surface of these nanoparticles. I didn't show here the very good quantum efficiency of these nanoparticles, even though they are very small. But what was interesting is that when we introduce hydrogen peroxide inside Tris buffer, so it's colloidal solution inside Tris buffer, we observed quenching of luminescence intensity depending on the intensity, on the concentration of europium, and for 50% and 100% of doping, this quenching was very strong, and for this best sample, the quenching constant was rather high, and the limit of detection was 1.6 micromoles of hydrogen peroxide. I know that this is not a huge number when you compare with some classical analytical tools like mass spectrometry, but one should bear in mind that we are dealing with optical detection with very simple instrumentation that can be implemented in small spin-off companies, and the device for reading luminescence that is excited at one wavelength and detected emission on a single wavelength is very straightforward and simple. And why is that so important? It's important because our nanoparticles were not cross-sensitive to anything else except to hydrogen peroxide. And then hydrogen peroxide actually product of enzymatic reaction of enzymes from the class of oxidases. And there are so many of these enzymes So let me explain in short. For example, if we want to detect glucose, then we add glucose oxidase, its counterpart enzyme, and as a product, we will get hydrogen peroxide, and it will quench emission. And via quenching of hydrogen peroxide, we can determine the concentration of glucose, for example, in blood. And on the left side, you can see the example of the measurements where we, at the same time interval, add to one sample hydrogen peroxide, and to other sample where we put glucose oxidase, we add glucose. And you can see that it follows the same, the intensity of fluorescence follows the same pattern. Here's the Stern-Volmer plot. It's a little bit different because the reaction never ends, so it's exponentially approaching to zero, but it's not a problem since you can always calibrate for this some element of incubation. You get excellent plot linearity, so you have a way that in a very simple manner you can detect the glucose from your sample by measuring fluorescence. And the idea was with Professor Volweis at the time, and we will now proceed with this idea, to make sensors. So it's easy to make these assays to measure glucose in this way, but you know that in hospitals you have this monitor that measure your blood pressure, your heart pulse and rhythm and so on, but it is also important to have these monitors for continuous measuring of some other things which are related to the patient's conditions. And what's interesting with this, so the idea was to put this sensor in some hydrogel connected with optical fibers that then will be implemented below the skin, and that enable measurement of, let's say, glucose, or I will explain you just in a moment some other things. And I hope that we will do this in the near future. But what's interesting also here is that you can just change the type of enzyme, the type of oxidase, and then you can, with the same principle, measure some other properties. For example, if instead of glucose oxidase, we put cholesterol oxidase, then in reaction with cholesterol, it will also generate hydrogen peroxide. So by changing only one component of our assay, we can perform measurements of different things using the same experimental setup with the same excitation, with the same emission wavelength, so we can make very small portable measuring system, and then just by changing the assay, we can do a lot of measurements. And this is not the end, since I can put two pages of different analyses that can be measured. Some of them require, for example, 2 enzymes to complete the reaction. For example, triglycerides require lipose to convert triglycerides to glycerol, and then glycerol oxidase make the final reaction. So we can do measurements in the same way, maybe 100 different analytes. Okay, so this is an example of nanoparticles for measuring for chemical sensing, and then nanoparticles and for biomedical and biothermal imaging. So the idea is to have one nanoparticle that can serve as a fluorescence luminescence imaging agent, but also that can provide photothermal heating to ablate, to destroy cancer, and also to serve as a way to measure temperature of the cancer cells. So in photothermal treatment of cancer, it's important to raise the temperature of malignant cells to draw them in so-called programmable cell death, apoptosis, but not to overheat them to go to necrosis, because necrosis can poison the body. So we did a lot of these nanoparticles. As you can see, 2 of them were particularly interesting. So gadolinium vanadate with neodymium and neodymium with ytterbium aluminum garnet, very famous host, because both of them have very good absorption peak at 808, where we have very cheap 808 lasers, and where, by the way, tissue, this wavelength provides the less damage to tissue among all other wavelengths. So what we did, firstly, we first wanted to explore how much heat we can generate with our nanoparticles, and here we have different doping levels. And on the lifetime measurements, we can see the lifetime rapidly decreases with the amount of neodymium up to stoichiometric amount of neodymium. This means when we have huge non-radiative recombination, but still emission, then this non-radiative recombination goes into heat. And you can see here the cuvette with the dispersion of nanoparticles excited by 790, 808, where this absorption is the highest, and on 820. You can clearly see the increase in temperature. This is measured by thermovision infrared camera. So you can clearly see how that the heat is generated inside the cuvette with the nanoparticles. And here is an example of thermal imaging of the cuvette while we are scanning tunable laser through the absorption peak of these nanoparticles. And you can clearly see how this heat is rapidly generated. We did this research with a famous group of Professor Daniel Jacques because we can do most of the things that we could not do in vivo measurements with small animals. That's the main reason, and he has all the facilities and huge knowledge to perform this. So let me go to this part of experiment. So we injected our nanoparticles, and lanthan fluoride nanoparticles were kind of standard until we show results with this type of nanoparticles. As you can see, the temperature that was generated by our nanoparticle is much higher for the same laser intensity that we put on the tissue. So these nanoparticles are 2 millimeters below the tissue depth, and then we are taking thermal imaging of the tissue on the surface, and we can clearly see the heating of the tissue. So this means that we are able to use these nanoparticles as the heating nanoheaters inside the biological environment. And here on the right side, you can see the results of measurements when we introduce these nanoparticles into the cancer of the mouse, living mouse. On the left here, you can see the optical image. Here is the infrared image, and you can clearly see luminescence because it's infrared. It can penetrate outside of the body. And this is the merge of these two images when you can see the mouse with the illuminated cancer. And on the right side, you can see thermal measurements. After 4 minutes of irradiation, we raise the temperature, and we use neodymium 3+ as a Boltzmann thermometer to measure distribution of temperature inside the cancer. So these luminescence can serve also as a agent for luminescence imaging, as agent for biothermal imaging, and also as a photothermal agent to produce heat inside the biological environment. There are some examples of intracellular measurements. So people today are now able to measure temperature distribution inside the cell. And let me just point out that when you have gadolinium inside, it can also serve as a T1 positive magnetic resonance imaging. So they are very versatile nanoparticles. And so I have also two short examples. One is of using excitation emission spectra, fluorescence, autofluorescence of food to determine their biological and geographical origin, and to investigate is it real or fake. In case of honey, it's highly important to have to determine is it real honey or fake honey. There are so many fake honeys, and also to have botanical origin of honey. So the standard method to determine whether it's acacia or linden is to take and observe a pollen a particle inside by the microscope. So it's time-consuming and very expensive. And Chinese are really amazing in making fake products. So they take this very cheap rice honey, they completely filter pollen from it, and then put some other pollen, and then you sell to you. And European market is full of these fake honeys. And also we did it with beer. We applied something that mathematicians will probably like a lot. It's parallel factorial analysis, which Professor Rasmus Broch, who is a pioneer of this method, and also from Copenhagen, he also developed several softwares for use this, and I send my students to Denmark, and they spend some time and they learn to do this. Unfortunately, or fortunately for them, once they finish PhD, they get very good appointment in some American companies that are working here in Belgrade, which are related to this field and have huge salaries. So somehow we stopped this research, but I'm planning to continue it. So let me give you one example here. So we can measure intact honey, put in cuvette, do excitation emission measurements. So excitation emission matrix is a series of emission measurements at different excitations. Prepare this in 3D, so-called 3D matrices. It can be tensors in some cases, not in this one. Remove Rayleigh and Raman scattering from them, do some necessary normalization, and then apply parallel factor analysis. By the way, this paper is actually published in Food Chemistry, and it's a Essential Science Indicator, highly cited paper in the field. So this method, which is very good because it provides unique solution, is able to decompose excitation emission matrix into emission and excitation spectra. This excitation spectra of the number of components. The main problem with this method is always to determine how much components the model should have. But then you can do split half analysis, and you can do validity of your research, and then we are able to determine which components they have the most responsibility for the luminescence of honey. These are listed on the left. These two, furosin, hydroxymethyl fulfural, is actually very important also because they are product of Maillard reaction, and so they can give information about the age of your food product and whether product undergoes some thermal temperature treatment. We can do relative concentration of these components in our sample, but if we calibrate once with some other analytical method like mass spectroscopy, then it can provide this not relative but absolute values of the concentration of these compounds inside our samples, and then we can perform some other things like partially square discriminant analysis. So we are able to discriminate completely from the fluorescence spectra fake and real honey, and also to determine botanical origin with very good results, not perfect. The problem is this meadow honey, which composes of different flowers. But if we had more samples, the probable results would be better. So basically, we have a tool that you can take honey, put in 3 milliliter cuvette, do 1 minute of measurements, go through software, and you can determine whether your honey is fake or it's a real one. And before I go to the last example, I want to say that we also did very good research on beer. It was a very happy time in our laboratory with beer. It's because we have this company here, a lot of pubs, which are called beer drinkers. So they have beers from all around the world. You can, I don't think that there is any beer that they don't have it here. So we take about 400 different bottles of beer, and you need only 3 milliliters of beer to do experiment, and we were somehow sorry to waste the complete bottle. But the result was good. What's interesting is also that, for example, not that we can just find from the spectroscopy that beer is pale or ale or whatever. The same type of, for example, of Heineken that is produced in Germany and in Serbia, and then there is a difference. We can tell from which geographical location the beer is coming. So it's kind of amazing. And the last example, sorry if I go over the time, is the use of synchronous luminescence spectra. It's kind of similar to excitation emission matrices. The difference is that you scan both excitation and emission monochromators with the same wavelength difference or energy difference. There are two ways, and then you obtain the total emission, the total spectra, and then this is with very simple partial least square discriminant analysis, we are able from one measurement to discriminate between melanoma, nevus, and normal skin. So we actually now apply for some money to get to make a device which will be portable. We started to make device right after we finish this research, but the company was actually asking not to be related to skin cancer, but to be related to cosmetics because they can sell both. So we developed a new dermoscope for them, and now we are going back to something but at least we think it's more important. It's the detection of melanoma in its early stage. So thank you so much for your time and for inviting me.
Thank you, Miroslav, for excellent presentation. So we are now going to the question and discussions, and please welcome to the first. I see that our Vladimir Pankratov is first, who is will do question. Please,
Yeah.
Vladimir.
Hello. Yeah, hello. Hi, Miroslav.
Hello.
It's very nice to see you.
Yes.
I would like to, first of all, to give some comments, not question, but comments, that Miroslav group and group of Laboratory of Spectroscopy of Institute of Solid State Physics, now we have very intensive collaborations, and we have maybe already 2 or 3 joint beam time experiments and BESI and MAX4. Unfortunately, Miroslav didn't show this recent results which we obtained and the beam time, but I hope he will do it next time. Yeah, because this collaboration is really fruitful and a lot of results obtained. And I would say that from previous beam time in November, already 5 publications are in press. Yes.
Yes.
Okay, thank you.
Yes, and maybe a short question to Miroslav. As expert in luminescence thermometry, you what is your opinion? Is it prospective field for the luminescence materials now, or it's already well developed, well studied field, and not necessary to apply big forces for this field? What is your opinion?
Well, it's a question that I asked myself 2 or 3 years ago. I thought that it's maybe at the end, but it's not actually. It's something else. It's moving to engineering. It's moving to its primary objective, to be metrological tool. So we have different applications require different materials, different wavelength spectra, so the field is still open. The main idea is to now develop new ways to read temperature from spectra that will provide better accuracy and precision. So it's not dead. I think that it will still exponentially grow.
Okay, thank you. Maybe we go to the next question. Thank you very much. So next, Andrejs also has a question. Andrei. Please, microphone, Andrei. Microphone.
Yes, audio, yes. Okay, thank you very much for a very nice presentation. I'm not an expert in luminescence, nevertheless, I get a great pleasure from it.
Thank
you. And maybe therefore I have some two questions actually. First question about chemical sensing. What actually was sensed? The chemical compound of some material, or yes, what was the result by this spectroscopy? It was measured, hydroxide, peroxide, but what was the result? Okay, we know the luminescence function of concentration is okay, but if we are speaking about chemical sensing, then I propose that it means that we sense some chemical composition of some unknown compound, or it is not right?
Yeah, almost right. So it's a concentration of some chemical.
Yes, but it
is
is
analytical chemistry. So in this case, for example, we put a drop of blood and we determine the concentration of sugar in the blood of glucose. Or, as I explain you later, it can be triglyceride, it can be cholesterol, it can be anything.
Yes, but you are
okay. Maybe next question, Andrei. So
you are measuring some substance which is already known, but only you are measuring its concentration, like sugar. But
yes,
not so that you are revealing what is the composition.
No. But you know this analytical chemistry is.
Okay, I think it's maybe very sophisticated.
Okay, thank you. Let's go to the. Thank you, Andrei. All this, Andrei. Let's go to the next question. It is Anatoly Sharakovsky. Anatoly, you're.
Yes, thank you. Thank you, Miroslav, for very interesting presentation. It's nice to see you in this community. My question is actually first comment. I didn't know about this chemical sensing of beer that you made. So maybe next time when you do these kind of projects, you could add us as partners, even without funding.
Okay.
My question is about luminescence thermometry. How widely actually optical temperature sensors are used in the industry, and is it still a growing market? Or I mean, a lot of different experiments and papers are published in this field, but how they are really brought into industrial setting?
There was actually now this EU funding for metrology, and they were pursuing one project to make some kind of metrological standards in biomedical industry. So there are also for Mada. It is applied more and more. So there are some fields which you cannot measure temperature by any other means. And these are important. For example, there are no standard methods to measure temperature distribution if 2 points are separated by a large amount of 1 micron. And you want to do nanotechnology. How can you do nanotechnology if you cannot measure temperature with a better resolution? Or in engineering, for example, you want to have distribution of the temperature on the surface of the piston and then you cannot put resistivity or some thermocouple. You need to do by optical means to coat this piston with the phosphor or something. So there are so many applications, and it's really, really growing. There will be Congress on phosphor thermometry in industry that will be in, I think, July in London. I can share with you if you want the link. I will not go because I will go to France because it's a conference devoted to late Professor Georges Boulogne. But this is the good place to go if you are interested in applications of luminescence thermometry in industry.
Okay, maybe. Thank you. So let's go to next question because time is running. Gita, please, your question.
Yeah, thank you very much. So, as a scientist from the plasma research field, I like to hear that light luminescence is used for so many applications, but I have the question, how can you advertise or propose your methods? Because in every of these fields, I think there are like alternatives, like for chemical analytical chemical analysis, the same for the temperature measurements, because also in gaseous phase we have a lot of problems how to interpret it. Also the decomposition issue, what you mentioned, even in plasma you have a lot of methods and problems how to find the real spectral line profile. So what arguments can you use in comparison with other methods?
So thank you very much for, my first neighbor is Professor Zoran Petrovic. Maybe you know him. He's an academician here in Serbia doing plasma research for many years. We've been discussing. I don't think that for plasma application it's a real thing, because plasma will destroy materials, probes. But other types of sensing become standards. For example, chemical sensing with luminescence nanoparticles overtakes now electrical methods and some other methods when you want to have cheap, available measurements. Of course, this gas chromatography, mass spectroscopy is something else. And for thermometry, it is not used for to substitute classical thermometers, but it's used mainly for nano research, for biomedical research, to monitor temperature inside living objects with fluorescence that goes in these biological transparency windows. For in harsh environments, let's say in turbines, where you have fluids and vapors and so on. So it's not for the mainstream thermometer. It will not substitute mainstream, but for specialty measurements, it has.
Okay, thank you. So maybe last question, I also give one. So you show synchronous radiation research. We have for many years worked on XEL, X-ray excited optical luminescence. As you now collaborate with Vladimir Pankratov, are you looking on X-ray luminescence to see with synchrotron some interesting activities?
Yes, there is a part, this is at 50-50. So one is for phosphorus. We have one proposal which just fell short 0.1 point for this European Pathfinder funding, is to have nanoparticles that will emit in UVC and also act as to enhance X-ray radiotherapy. And for this reason, we are looking to develop.
Okay, nice.
Yeah, so it's. But we will get the project next time. It's
Okay.
Zero.
Thank you. Our time is running. Sorry but really last question. It is Andres now. Okay. Andres Sanspok.
Yeah. Thank you very much for presentation. What do you think about this method to detect nanomoles and picomoles of biologic substances? Thank you.
Well, okay, but depends. It can be done with some luminescent materials, with semiconductor and quantum dots on nanomoles. It's regular, but below that you need some classical analytical methods like mass spectrometry, gas analyzer. I don't know that with luminescence you can go to such a small concentrations. Maybe it's possible.
Okay, thank you. So time is running, and thank you once more, Miroslav, for excellent, interesting
presentation. Thank you for inviting me. Really an honor.
Okay, we think on good collaboration in future.
And hoping to see you in Belgrade soon.
Thank you. Thank you.
Have an open invitation.
Nice city, I remember. Okay.
Yes.
Let's go. Unfortunately, we need to go to the next our presentation, to the presentation of our new foreign member of Academy of Science, Dr. Jāņa Timošenko. He is here. At this moment, he is in Berlin, and some short introduction about his activities. First of all, I am glad that Jāņa is elected as foreign member of Academy of Science, as he has finalized his master degree in my laboratory. I was in this period head of EXAF's laboratory in 2010 with some. Unfortunately, we not have all published papers on germanium isotopic effect. We have see femtometer, some activities. So next one, he has finalized his PhD thesis in 2015 with under supervising of our academician Alexei Kuzmin. This is excellent PhD work with development of reverse Monte Carlo analysis of exospectra and with analysis of also such interesting materials like perovskite rhenium 3 oxide with hydrogen effect, is also many things. And after that, he has had some postdoc position and also from 2018, he is in Friedrich-Haber Institute of Max Planck Institute in Berlin, working on catalytic materials with EXAF's method. Jānis has published about, I don't know in this moment, but it was previously in Google Scholar, 120, maybe 100, maybe more, 30 papers with a high Hirsch index 41 and with very high citation. But important, the quality of papers is Nature communication, so on. And now he will done presentation on his topic on revealing and steering the dynamic structure of electrocatalysis by operando spectroscopy. This is a synchrotron research. It's very popular now. Before it was in situ, now in operando method of X-ray absorption spectroscopy. So welcome, Jānis, please. Sāciet, lūdzu.
All right. Thank you so much for the introduction and for the invitation to present some of our work here. So very nice to present in front of this prominent audience. I hope you can see my slides well. And
yes, thank you.
Perfect. Yes, so as mentioned, right now I'm a group leader in a Friedrich-Haber Institute of Max Planck Society. And for our institute, the catalysis plays historically a very important role. So originally this institute in German Empire times was called as the Institute for Physical Chemistry and Electrochemistry. And its founder was famous Fritz Haber. It's also first director of this institute was Fritz Haber, who developed this catalytic process for ammonia production from nitrogen and hydrogen. And from this effort, he received also Nobel Prize shortly after the First World War. And this is one of the 5 Nobel Prizes received in our institute. And closely related to this work is also the most recent Nobel Prize for our institute, awarded to Gerhard Ertl, who also received his prize for his study of more or less the same catalyst and more or less the same reaction, just using different approach and different techniques. So, of course, catalysis science comes in different flavors, and the objective of my group is working on operando investigations of transformations of catalysts, and we're using different techniques and different tools for this purpose, but most of them are related to synchrotron-based science and X-ray-based approaches. So I myself am not a chemist, but we're trying to apply different physical methods for understanding the systems which are important for different catalytic and chemical processes. So why in general should we care about catalysis and how catalysis actually work? What do they do? So you can imagine that catalyst is sort of assembly machine which takes reactants and converts them into the reaction products, so helps the reaction to take place. And the way how it works typically is illustrated just by this diagram where we show the activation energy without catalyst and with catalyst, and then presence of catalyst just lowers the activation barrier for the reaction, which means that you need less energy, less effort to make the reaction happen and convert your reactants into the reaction products. So this sounds simple enough. However, this is also a huge industry. So chemical production in general is a multi-trillion industry. So it's a huge scale and huge amount of money involved. And about 85% of all the chemical manufacturing processes require some sorts of catalysts. So it's a very broad topic which covers everything from different production of fossil fuels or conversion of fossil fuels to the catalysts which are inside your car, to converting exhaust into something less harmful, to also some new systems which are, for example, used for hydrogen production, green hydrogen production using green source of electricity and electrochemical water splitting. So there are very many different flavors, but all of them rely on catalysts, and all of them constantly are looking for better and better catalysts to make these processes more cheap, more economically viable, more efficient, and more environmentally friendly. So what makes a good catalyst? So good catalyst should be active, so it means it has higher reaction rates, but it's not the only condition. So we also need to keep in mind that the catalyst should be selective, which means that if we have reaction which has more than one possible reaction product, and you want to obtain only one of them, so you want to have catalyst which facilitates one reaction branch and does not allow another competing reaction to happen. The catalyst should be also stable, so you don't have to replace it every week or every day. But also ideally it should be cheap and earth abundant and convenient to handle. And of course, non-toxic would be also a nice property. So all of these properties often are contradicting to each other, and it's not easy to satisfy in practice and to find a catalyst which works for all of these possible applications. And that's why catalyst development and search for new catalysts is still a very much active field and requires a lot of effort and ingenuity and new approaches. So one famous example how it historically works, again, is related to this context of Fritz Haber process and production of ammonia. So soon after Fritz Haber patented his process, it was clear that to make it industrially viable, these catalysts which he was using, and he was using osmium and uranium catalysts, are not really what you can do on large scale. So there was open challenge how to optimize this process and how to make better catalysts for this particular reaction. And BASF, this gigantic industry company in Germany, it hired Alvin Mittasch to find a better catalyst for this reaction. And he noticed that some iron catalysts can work well for this process, but only particular iron ore from one particular region in Sweden, which actually was working. Pure iron was not working for this process, but really one specific iron from one specific town in Sweden was working fine. So it took him about 6,000 or 7,000 different experiments, and he tried more than 2,000 different catalysts to try to replicate this naturally occurring mineral in the lab and obtain a catalyst which is more or less used still also nowadays in the industrial production of ammonia. But even now, there's still many questions remain about why exactly this catalyst works and how exactly it works and what's the most necessary component into this catalyst. So it's still an open problem despite its huge industrial relevance and more than 100 years of research on this topic. And of course, if you look about this Mittasch screening of different catalysts, where he basically empirically tested out so many different catalytical systems, question arises, is there a better way how we can find better catalysts and how can we optimize the existing catalysts to achieve better performance? So one specific reaction I will be talking about now will be not related to ammonia production, but something maybe more environmentally friendly, namely CO2 electroreduction. So the objective here is to convert CO2, this greenhouse gas, into something more usable and into some useful chemicals or chemical feedstock or different fuels. And in principle, CO2 conversion is a complex process, but it can result in a broad distribution of different reaction products. So dependently on what catalyst you use and on your reaction conditions, you may get very different reactions starting from CO and methane and ending up with ethanol and ethylene and even more complicated chemicals. So which exactly pathway is chosen depends a lot also on your catalyst and also often on very subtle details of this catalyst. So the parameters like surface roughness, surface structure of the catalyst its oxidation state, its chemical composition, but also sizes, shapes, and morphology of catalyst nanoparticles. All of this can affect how exactly this reaction proceeds and what exactly will be the outcome of your reaction. Unfortunately, to make things even more complicated, all these parameters of catalysts, they do not stay the same in the course of reaction, but actually they do change. So often what you have is a complex catalytic system in the beginning, which converts completely under the reaction conditions into something else, which is still very complicated. And the challenge here is to establish the link between the structure of your catalyst and the desired properties of these catalytic materials. And this can be ideally achieved through some operando investigations. So one idea which we can pursue here is try to benefit from these transformations in the catalyst which take place in situ under actual working conditions, and somehow engineer or reaction protocol so that this transformation results in a desired structural motifs, desired surface structures, which would have some desired catalytical properties. So how can we design such process? Can we do it blindly, or we should use some guidance? And of course, it's very nice if we can have some rational insight into these processes which takes place in these catalysts when they are under working conditions, and have some insight from operando spectroscopic or microscopic techniques which tell us about what happens with the catalyst and how can we manipulate with these processes to obtain desired functionality. So one nice example from a few years ago was related to, again, CO2 electroreduction reaction, where we used copper oxide nanocubes as a catalyst. So these are very nice, very monodisperse cubic-shaped catalyst particles, at least in the beginning, in the as-prepared state. And our idea here was to try to manipulate with the properties of this catalyst by exposing it to a pulsed reaction protocols. So normally, when you're running CO2 electroreduction reaction, you're applying a static negative potential, which reduces your oxide nanocubes to some metallic copper state. And this is basically the end of your story if you do it under stationary reaction conditions. However, if you periodically interrupt your negative applied potential with short pulses of more positive potential, you can tune the oxidation state of your catalyst and play around with the surface structure of the catalyst which you obtain. And now, by just tuning the knobs on your potential state or just changing the duration of applied potential pulses, we can actually steer the catalyst into different regimes, where we can have completely metallic or nearly completely metallic catalyst which has thick oxide shells, or have some nice islands of oxide with peculiar oxidation states. And each of these different regimes have different catalytical properties, resulting in different reaction products, starting from the same CO2 molecule. So this was a very nice story, but today I would want to share maybe even more exciting or maybe a more interesting result, which I obtained more recently, again, in the context of this CO2 electroreduction reaction and running it under pulsed reaction conditions. So the system I'll be talking now are so-called single atom catalysts, or transition metal nitrogen co-doped carbon catalysts. So it's a broad range of different catalytical materials which can be synthesized in different ways. So one of the approaches illustrated here on this slide. But as a result, you end up with this carbon structure which has nitrogen incorporated, and this very characteristic 4-nitrogen site acts as an anchoring site for transition metal, where you can put different transition metals. It can be nickel, it can be iron, it can be copper, it can be tin. So dependently on your reaction in mind and on your application, you can try these different metals here. And if you run this CO2 electroreduction with this catalyst using these different transition metals, you can get different reaction products. So you can get more CO for nickel, more hydrogen for iron-based catalyst, or if you use tin-based catalyst, you can get even some formate. In particular, nitrogen, nickel-based and NC catalysts are actually currently very actively studied in the context of CO2 electroreduction, because they can convert CO2 into CO with nearly 100% selectivity, which is very rare and actually quite nice from a technological perspective. So, but if you want to understand how these catalysts adapt to reaction conditions, how can we do it experimentally? And for that, we actually don't have many different techniques available, because these catalysts are so small that you cannot really see them in microscope. or even in electrical microscope under operando conditions, they also don't produce any X-ray diffraction peaks. So basically, almost only technique which you can use for this purpose is X-ray absorption spectroscopy, which of course for us is very nice because this is a technique we are really, it's or very close to our hearts. So in general, X-ray absorption spectroscopy technique is a local structural investigation method which provides you with information about the local structure, so electronic structure and atomistic structure of the material. So and typically, we distinguish two regions here, so X-ray absorption near-edge structure and the extended X-ray absorption fine structure, so XANEs and EXAFs, which encodes information about the chemical state of your catalyst and its atomistic structure respectively. So both these XANEs and EXAFs regions will be useful for our discussion in the next slides. But importantly, another important advantage of XAS is that you can do these experiments quite easily under operando conditions. So you can measure your catalyst under actual working conditions in the presence of electrolytes, in the presence of applied potential. So you can really see on the fly how the catalyst is responding to changes in your electrochemical protocols and what happens with its structure, especially if you can have some idea about what could be possible structural motifs which you can encounter. So this is typical electrochemical cell we are using in this experiment. So it's actually very simple. It's just basically cube filled with electrolyte, potassium bicarbonate in our case. And then the catalyst is deposited on carbon electrode and just taped with a tape on top of this lid. And we measure it illuminated by X-rays from the back through the carbon, through this Kapton tape. And we collect X-ray fluorescence signal from the catalyst under its operating conditions. So it's conceptually a very simple experiment, and it works very nicely for many, many different reaction conditions. What's nice here is that also with the development of synchrotron radiation facilities, we can actually do these experiments with very good time resolution, so up to 1 second per spectrum. And in this case, we can track really fast changes in the catalyst and obtain information about the changes in oxidation state, but also about the changes in its local structure. So coming back to this transition metal nitrogen co-doped carbon catalysts, we looked at them, different of these catalysts using X-ray absorption technique during several of our beam times in France, in Spain, and also here in Berlin. And actually all of these catalysts respond quite significantly to the applied potential. So you can see just by looking by eye without any analysis, the X-ray absorption spectra for each of these catalysts changes a lot when we apply the potential. So there is really significant structural changes. For different catalysts, different transition metals, these changes are somewhat different, and all of them are interesting and probably deserve its separate discussion and presentation. But today I will focus on this copper and nitrogen carbon doped catalysts, which are actually quite different from the rest of this series of catalysts and have very intriguing and interesting properties. So if you look at what happens with this copper NC catalyst under applied potential, under applied negative static potential, again, even if you're not expert in X-ray absorption spectroscopy, just by looking at the spectra and comparing them with the spectra for references, you can see immediately that in the beginning you have some sort of oxide-like or cationic structure, which might have similar local environment as copper in copper oxides. But under applied potential, the spectra look completely different and actually matches very nicely spectra for copper foil, but with lower amplitude. So it tells us that under working conditions, under static CO2 electroreduction conditions, these copper single atoms actually don't remain single atoms, but actually migrate and somehow cluster together, forming copper and nanoparticles. So this already is quite interesting, but we also, of course, now can track this transformation in time-resolved manner. So by using this operando quick EXAFS method, where again we can measure this process with resolution of up to a few seconds, we can track very nicely how this formation of metallic copper-copper bond occurs in this material and how this cationic copper-nitrogen bond is gradually diminished during this CO2 electroreduction experiment. We can quantify this transformation. We can extract information about how many of these copper species remains in cationic state and how many of them are converted into the metallic clusters. And you can see that it's process which is fast in the beginning, so this initial transformation takes 3 minutes, but then there is slower gradual changes on the scale of up to 5 hours, where the catalyst is still evolving and transforming into this more and more metallic state. So this information we can get just by looking at X-ray absorption energy structure on hexanes and comparing it with the spectra for reference materials. But if we manage to extract also EXAFS data and do the fitting of EXAFS spectra, we can extract information about particle sizes. Specifically, what we extract from EXAFS is the average copper-copper coordination numbers, which we see are actually clearly changing a lot during this experiment. So we start from 0 and ending up with something about 8 point something. And then using simple models, we can link this average coordination number, which basically characterizes your surface to volume ratio in your nanoparticle. We can link this parameter to specific particle sizes in nanometers. So in this particular case, we see that these particles which are formed are about 1.3, 1.5 nanometers in size under static reaction conditions. What is interesting, it's actually quite generally the case. So you can look it up in this process studied in several papers, not just ours, for particle catalysts synthesized using different approaches. And all of them more or less converge to this more or less the same particle size of about 1-2 nanometers under similar reaction conditions. Also importantly is that not all of these copper single sites are converted into this metallic catalysts, but some of them, about 20%, remains in the cationic state, which again is something quite common across many different studies and catalysts with very different synthesis procedures. But perhaps the most exciting or intriguing properties of this catalyst is that this transformation into the metallic particles is completely reversible. So as soon as you remove the applied potential, the catalyst actually reverts back. So these metallic copper clusters are gone. And so of course, was initially very confusing because you can make microscopy image of a catalyst before and after the reaction. And in both cases, you see that there are again these only single atoms present. You don't see any of these metallic nanoparticles, which you saw in the in situ and operando investigations. So in this regard, this system actually a very nice example of why it's important to do this operando and in situ studies, just because, as you can see in this case, just by looking at the catalyst after reaction, you can get completely misleading picture about what's actually happening with it under reaction conditions. And of course, the process itself is very surprising. So we can probably understand why these single sites tend to cluster into the metallic particles. However, it's harder to understand how these metallic particles can be pulled apart and form again back these singly dispersed sites. And again, it's important to emphasize that it's really formation of original singly dispersed sites. It's not oxidation of particles. It's not dissolution of particles. It's not appearance of some new species. We applied different techniques, so X-ray absorption method, but also more advanced X-ray based methods to study this process. And in all cases, we see that final state of the catalyst after we remove the applied potential is basically indistinguishable from the original state of the catalyst, where we have this nice singly dispersed copper sites. So we have highly switchable system, which can be switched between the metallic state and cationic state back and forth, basically how many times we want. So of course, it was interesting for us to see whether we can manipulate with the system using our potential pulsed reaction protocols. So the idea here again was similar to what we did before with these copper cubes and larger copper catalyst particles. So instead of applying static negative potential, we want now to apply pulsed reaction protocols where we interrupt the negative potential with short pulses of anodic potential and try to see how it can affect the structure of the catalyst. And again, just by looking with the naked eye on your spectra, you can see very nicely that X-ray absorption spectra follow very nicely the changes in the applied potential, and we see the periodic changes, periodic switching between the cationic state and metallic state of this catalyst, which in this case takes place on a scale of 30 seconds. By using time-resolved X-ray absorption spectroscopy, we can also identify how many of the catalyst is converted into these metallic clusters and back into the cationic structures. And we can also track how the particle sizes changes in time in this process. So we see again this changes in the copper coordination number from 0 to 8 and back to 0 as we go along this pulse reaction protocol. Now, dependently on the duration of applied pulses, we can actually easily steer the system in the sense that the amount of cationic copper which remains in your cluster, in your system, actually depends strongly on the duration of applied pulses. So in this figure, we compare 6 different experiments where we did measurements under static applied negative potential and under pulse reaction conditions with 30-second durations for negative and positive potential pulses, with 60-second negative pulse and keeping the positive pulse again at 30 seconds, and so on. So 8 seconds, 30 second, 4 seconds, 30 second, and 2 seconds, 30 second pulse combination. And in each of these cases, you can see very nicely that this average copper oxidation state actually quite systematically changes with the duration of applied potential pulse. Furthermore, if we analyze the particle sizes, we can see that also this average copper coordination number actually also very nicely changes from this original value of about 8 point something, which we saw for the static conditions and also for longer potential pulses, but we can reduce it to a coordination number of about 1 or 2 when we go to shorter and shorter potential pulses. So this means actually in this F condition, we actually really have very, very tiny atomic clusters because coordination number of 1 means that each copper has on average just one another copper atom in the vicinity. So it's basically copper dimers, which we have in this catalytic material. So by combining all this insight from operando investigations, we can conclude with a simple model of what happens with this catalyst. So we start with the thinly dispersed structures, and under negative applied potential, we form first very small atomic clusters of copper dimers, trimers, and so on, which then gradually can grow into bigger and bigger particles. But once we apply positive potential, these bigger particles fragment back to the smaller ones, and then eventually these smaller particles again are pulled apart and form original ultra-dispersed, thinly dispersed cationic copper sites. And once we repeat this pulse sequence, we repeat all of these 4 processes again and again. By extracting the characteristic times for these transformations, we can actually predict how many of these different species we will have dependently on the duration of applied pulses. So here in this plot, the black line shows the concentration of cationic, thinly dispersed copper sites. The red line shows the concentration of larger copper particles, and the blue line shows the concentration of these very small dimers and trimers of copper. Dependently on this duration of pulses, you can switch in which regime you are. And these characteristic times of 16 seconds in this case are just the typical reduction and oxidation times for these copper clusters under this applied combination of negative and positive potentials. So of course, we can now steer the structure of this catalyst, but how it reflects the catalytical properties. So we did the catalytic performance measurements for this catalyst under different pulse conditions, and we saw actually very interesting and non-linear changes in the selectivity of the catalyst. So if we apply very short potential pulses, the catalyst mostly produces hydrogen, while under longer potential pulses, it's some combination of hydrogen, CO, and methane which is being produced. But in this interesting regime where we have a contribution of very small atomic clusters, we can see actually quite non-linear changes in the selectivity, and in fact, we see pronounced formation of methane in these conditions. So this allows us to propose quite simple explanation for the observed trends is that these thinly dispersed sites are good for hydrogen evolution, but not really good for CO2 conversion, while these bigger particles are good for production of ethylene and CO, but these very, very small clusters are really good for production of methane. So depending on what reaction product you need, you can actually easily switch between the structures of the catalyst just by changing the parameters of applied pulse protocol. And again, it's very interesting that these behaviors seem to be universal across very different systems. And we can find also publications where another researchers stabilized similar small copper clusters using different approach without applying potential pulses, but by changing the composition of their catalyst in the synthesis, and they applied very similar trends, very similar correlation between the production of methane and the presence of very small ultra coordinated, low coordinated copper sites in copper dimers and trimers, which they supported also by DFT simulations. On another hand, this regime which we enter when we're applying longer potential pulses where we form bigger particles, here this observed selectivity trends matches very nicely with the general observation about the size dependency of CO2 electroreduction, product distribution on particle sizes, which were again obtained in our earlier studies using bigger particles produced using completely different synthesis approaches. So it really seems to be that this pulse reaction protocols allow us to bridge between these different studies of ultra small systems and studies of larger particles. And in our case, we can easily switch between these regimes back and forth on demand just by changing the parameters of applied pulses, and of course, tracking these transformations using operando spectroscopy methods. So with that, I came to my conclusion. So pulse reaction protocols and this non-equilibrium reaction protocols is really nice and new trend for steering the structure function of the catalyst, but of course it requires some guidance from operando spectroscopic techniques. In this particular case, we have demonstrated that by going to this regime of ultra small metallic clusters, we can get properties which are not typical neither for larger particles nor for single atom sites. So we can get very unique functionalities just by playing with the parameters of our experimental protocols. And of course, insight from operando methods allow us to decouple the contributions of different species and get some mechanistic understanding of these trends. So with that, I would like to thank all my group and my collaborators for their contribution and all of you for your attention. And if you have any questions, I'm more than happy to answer them.
Okay. Thank you, Jānis, for excellent presentation. And for us, it's especially interesting for the development of spectroscopy in this field. So I will start, we move to discussion and question. I will start with my first question. I haven't seen other question at this moment, but what is the concentration of copper atoms on the surface? Can you, because if you speak about single atom, so and it is on surface, and what is really it need be very high sensitivity. What is the concentration of atom surface?
So in this particular study, it was probably below 0.1 milligram per square centimeter of copper. Actually, next week we have another beam time where we will look into this system and we'll try to see if what happens if we go to higher concentration. So in principle, it seems to be that we can put even more copper and it will still behave in a similar way. But this we still need to check.
But you put copper as a product that is this. It look like some layered structures that is like.
So the original catalyst has this copper incorporated into this carbon structure. This carbon is sort of distorted, amorphous, ill-defined. Then the loading of copper, we can estimate it's about, like I said, below 0.1 milligrams per square centimeter.
And during reaction, copper is lose its position. It's give free this position like look like porphyrin, some like, and moved to form the copper nanoparticles.
Yes, so it forms these copper nanoparticles, but they still seem to be interacting with the support because otherwise they would not be pulled apart once we remove the potential. So we believe that the key to this reversibility is this particle support interaction. So it's a combination.
But in this case, its position of copper, it is like vacancy. It's go. If
so in the prepared catalyst, copper is kept here in place by the copper nitrogen bonds with the nitrogen dopants into this carbon structure. So it's a very commonly observed structure. And then under applied potential, yes, it forms in this metallic class.
Okay, thank you. So let's go to the next question. Your previous supervisor asked you a question. Alexei, please.
Yes, thank you. Thank you. First of all, yes, thank you very much for a very, very nice talk. It's really top-level research, sure. And I have two questions. First question is probably very simple for you. What is the role of this substrate? Is it really, it can change the reaction, or it is, let's say, just participating like a place for the reaction? Do you know something about this? For example, if you modify the substrate, yes.
Yeah, it's important to check whether support itself is not doing any catalytic activities. And we did this experiment. So in principle, it does a little bit of CO2 conversion even without copper, but the reaction rates are much lower than when you put copper on top of it. So it's not completely innocent, but it's certainly copper does the main job here in this reaction.
Yeah, but for example, the size or the shape of this copper nanoparticles, does it depend on the substrate, or they behave almost the same?
So this is what we're trying to understand actually in our current experiments, where we try to compare these copper single atoms synthesized using different approaches and from different precursors with different original structures. They seem to be quite similar, but we need to do more careful analysis to see how much we can tune that part as well.
Okay.
Maybe a second question, maybe, because for experts in catalysis, what is really the role of these electrical pulses at the atomic level? What really happens when you apply these pulses? Do you change the temperature, or you change some? Is it known, or this?
So in this case, we change somehow the thermodynamics of the system, so it becomes thermodynamically less or more favorable certain atomic configurations. So it's not temperature effect; it's really like energy changes of the energy.
Okay, energetic effect. Okay.
Yeah.
Okay, thank you. Now going to the next, Andrejs Siliņš. Andrei, please.
I think you're muted.
Microphone. Microphone, please. Okay.
Yes. Okay. Thank you. This was very interesting, but a little bit specific report. But I am interested in the following question. How did you measure the Faradaic efficiency? As far as I know, it means that it shows a part how efficiently electrons drive specific reactions rather than side reactions. I think it's not so easy to measure. How did you did it?
So Faradaic efficiency is calculated. You can go here. So we measure the amounts of CO2 which is converted, and then we measure the concentrations of the reaction products which we are getting. And then knowing the current and the charge which was transferred, we can calculate how much of this charge was used to produce certain products. So it's a result of calculation based on the concentrations of reaction products, which in turn is determined by gas chromatography methods.
Specific products to all products.
Yeah.
Thank you very much.
So, next question, please. Maybe I haven't seen all people who is. Okay. So, obviously, it will be interesting to have your presentation to see other topics that you have done many things, not only catalytic. So, have you what is your hot topic, what you plan to do? And also the second question, remember that we have worked on nano XT project to CC. Now it's in Nature or in Science. It was published single atom spectroscopy, really see one atom by X-ray. What your topic? What you plan to do in future?
So for us, so we have several things we have in pipeline. So one exciting development for us is that we now can do some of these operando experiments also in the lab-based setting. So we have now lab-based spectrometer for X-ray absorption measurements. So we can do some of these experiments also in our lab without going to synchrotron. And of course, it takes some development of experiment methodology and data analysis methodology. But in principle, we can look into very long-term evolution of the catalyst on a scale of days and weeks, which we could not do at synchrotron. And this sounds kind of maybe not too exciting, but it's actually really important for industry to be able to see this slow and long-term response of the catalyst to the applied conditions. In parallel to that, yeah.
As I understand, you have laboratory exospectrometers that you have by 2 years. So you can do this experiment in laboratory scale at this moment?
So we have already published one paper about studies of these copper cubes, which I showed before, so we can do these experiments now in our lab.
Okay, nice, very to see. So it is also, Gita, it's now your question about plasma.
No. Now I have more general question, which was actually due to your question. So as I understand, you work in Germany, right? Yeah, I think in Germany, in these Max Planck institutes, it's very important to have cooperation with industry. How it happens, how do you work? Normally you have interest from the industry side and then you start your investigation, because I think fundamental research is not so supported by the government. So it's mainly industry driven, just for our knowledge, because we suffer a lot in Latvia because we don't have enough cooperation with local industry. How it works in Germany?
So we have different modes of collaboration with industry. Some of them are these projects which are really initiated by the industrial partners, so they provide some funding and we try to find a common research topic which is of interest for them, but also not too boring for us. At the same time, there are also government-funded projects which kind of invite as a partners people from industry and us as a researchers to work together on the same project. And so sometimes there is also some government funding into this project. So it depends a lot also on the financial situation in Germany. So these industrial projects sometimes can be a bit more coming and going independently on how good the markets are for these industrial companies. But of course, we have very close ties with the companies which are here local in Germany and also.
Can you help us to work better with the industry? I mean, now you are the member of the academy.
I think it's of course, very much depends on finding this common research team. So if there is some thing which you believe could be interesting for industry, I'm sure that they will be very happy to hear about it, about your ideas, because they're always, of course, also very much interested in finding new ways how to make their life easier, the catalyst better, and even small improvement in the existing methods or small improvement in the existing catalyst can mean a lot of money for them. So it's, of course, they're always having an open eye for new research ideas, new method developments, and so on.
Okay, thank you. So we not have more questions, and thank you once more, Jānis, and thank you very much, Miroslav, also for two such interesting for us presentations. So it will be nice to hear, especially it's in English coming, that it's so more interest from abroad, from everywhere. So it's good experience. So Andrejs Siliņš, now your side finalized our meeting. What you plan to tell us?
Okay, from my side also, it was very interesting, and thank you very much everybody who participated in this meeting, and especially our colleagues who do the talks. Thank you. I hope that will be interesting also in future, and other foreign members will be able and willing to tell us about the scientific work in their laboratories. We could learn each from other lot of things. Now I would like to finalize this meeting once more. Thank you. And just for the next days, I would like to ask everybody, especially these colleagues who are here in Latvia, to fulfill the forms of how much you did in last year for our next meeting to reflect the work of our division in science. And from my side, that is now to finish, and I wish everybody Happy New Year, this one, and also next one, how to say, Red Horse year, which will come in February. And for people, everybody is invited in the next meeting in February. I am looking that Andrejs Siliņš would like to say also.
Yes, I would just ask when this next meeting in February will take place. What is it?
18th of February.
Thank you very much.
And as you are raising the hand, I would like to remind that you will be, Andrejs Siliņš will be involved in organizing our celebration of 80 years of our Academy of Sciences. Our president is inviting once more to take part in this group, how to celebrate that.
Until now, I have not received any invitation from the president to any meeting, but I am.
He is now organizing once more. You will receive invitation, I hope, as soon as next week. And I am looking for Donald Sachs also. You would like to tell something? Thanks.
I just wanted to say that this is 27th of February announced this academy best scientific achievements. 27th of February. This
that is another very important thing in February. Yes, that's right. But before that, it is also the meeting of Senate in 10th of February. That a lot of things will have in future days. And also a lot of things is now going on. In Riga is going this conference on quantum computing.
Quantum.
Yes?
Quantum computing, yes. And
yeah, that's conference. A lot of things is going on. And we are taking very important role in all those meetings, academy. And once more, I am happy that our foreign members are actively participating in the meetings and in our, let's say, work of our division. Thank you once more, everybody.